Hello everyone, my name is Luc Dando. I've been a designer of special mechanical and thermal machines since 1988, and I've been working as a consultant on concentrated solar furnaces since 1998. Today I'm going to present you my third concentrated solar furnace. For this machine, we are looking to obtain a very high concentration coefficient, as this is the first condition for reaching very high temperatures. With these temperatures, we would like to try out different craft applications such as forging, glass making, ceramic firing, and aluminium and bronze metal casting. Today, the highest concentrations are obtained with double reflection system. For example, Montlouis 1951 and Odeo 1969. The best concentration is provided when solar radiation is in the axis of a parabola. Very large sensors also increase concentration. However, the double reflections reduces radiant power. Here are my first two concentrating solar furnaces. The 1998 version with a concentration coefficient of 220. Each row of mirrors is fixed to a pivoting bar on a horizontal axis for the sense age tracking. For azimuth tracking, the unit rotates around a vertical axis. The 2017 version is a bread oven installed in Morocco with a coefficient of 90, sufficient to bake bread. It is an improvement on the 1998 model because this first model had focusing defect in the high and low position of the sun. Here's the kinematic solution that corrects two main lateral pointing defects. I've put these solutions in the public domain by publish it on my website in 2017 at this link. In this case, the mirror rotates on a second axis perpendicular to the horizontal axis of the support bars. This kinematic corrects the lateral pointing, but there remains a small defect in the vertical pointing. I have carried out a mathematical study to calculate these dispersions. It is available online under Creative Commons license at this link. Here you can see the current high temperature project. We hope to reach a power output of 10 kilowatts by midday with a concentration coefficient of 2000. Here you can see a power control panel for certain applications such as glass thermoforming. This project was initiated by the Common Causes 11 Association, or Cause Commune 11 in French. To sum up, the 1998 control kinematic causes significant scattering when the sun is in low or high position, but it's sufficient to bake bread. The 2017 kinematic corrects a very large part on this defect. The 2024 kinematics now presenter allow perfect pointing on both axes. What's more, we now have expertise in thermoforming mirrors into parabolic shapes. This represents a very important gain in concentration. For this new version, with the help of my son Damien and my friend Martin Bidard, I designed a new kinematic system which allows perfect pointing. While the frame tracks the sun in azimuth, a mobile frame slides parallel to the fixed frame and controls of the mirror in two axes of rotation, Y and Z. An operating rod attached to the mirror is driven by two specifically shaped holes for rotation in Y and Z. My aim here is to put this innovation into the public domain to prevent third parties from registering patents. Thus, we are inputting this innovation under Creative Commons license. For the energy and radiation calculations, I've asked for help of Simon Eibner. Simon is a teacher researcher at the École des Mines d'Albi and specializes in solar energy.
So, we perform optical modeling using Solstice free software, which has been developed by Mesostar. The software relies on integral formulation Monte Carlo. So here is the model on the left side. The parameters are given on the right side. So for each facet, which are parabolas, in fact, the focal can vary a little bit between 5 and 7 meters according to the distance to the concentrated spots. About the parameter, the sun model, we assume a pillbox model. The DNI is 850 watts per square meter. The elevation is 45. For the azimuth angle, in fact, the heliostat faces the sun. And the parameter that is a key parameter is the slope error. It takes into account orientation errors, and we performed sensitivity analysis, and so the values were 0, 3, and 5 milliradian. Let's move on to the results. So here are the flux maps that we obtained. Since Monte Carlo relies on statistics, results are always given with an error bar. So on the left side, it is the perfect case. So there is no slope error, and the maximum concentration is 2,900. So it is very, very high, in fact, but it is the perfect case. With a 3 milliradian slope error, the maximum concentration decreases to 900 approximately, which is still one order of magnitude higher than concentration for bakery application. So it is very, very high. And for a 5 milliradian slope error, it drops to 400 approximately.
Summary. What we have here is a system which, for the same surface area, can achieve better concentration than double reflective systems. Development of a two-axis mirrors control to increase concentration. Assuming no optical errors, the max concentration is 2,900. This furnace is under construction in Luxembourg, 11. It has been developed to craft foundry, pottery, glass blowing. We now have expertise in thermoforming mirrors into parabolic shapes. Thank you for listening.